Here we go. All right, welcome. I want to start by just reminding you that there's a quiz tomorrow in class. We'll have a quiz. So let's see. I haven't gotten around to posting a week 2 announcement. I'm going to do that after class. I got to get that up, and so there will be a schedule and stuff after class today. But if this happens, and I haven't posted the week 2 like announcement with the little snippet from the schedule, you can still look up the schedule yourself. So just a reminder: go to syllabus, and down here. It loads. You scroll down. The last page of the syllabus here is the schedule for the whole semester. All right, so you can look at week 2 and you can see, week 2. Yes, we didn't have class yesterday. That was Martin Luther King Jr. Day. Today, we've got a Zoom. It says review/flex day. We'll talk about that in a minute. Tomorrow, we're on campus. Tomorrow's our only on-campus day since we missed Monday. And we've got a quiz. I don't know if we'll spend the entire class period doing the quiz. I thought we'd spend some of it and then maybe do something else afterwards. Yeah, so there's that. And then later this week, we'll be working on 3.3 because 3.3 is kind of tough. All right. So yeah, just wanted to remind you guys that is there. And so if you're wondering what's coming up, there it is. Are you supposed to do the chapter 2 homework? There's a question in the chat. Yes, you are supposed to do the chapter 2. Oh, no, I'm sorry. Yes, but not until later. So we're switching the order. If you missed this announcement, we're switching the order of chapters 3 and 2. All right, so I'm starting with chapter 3, and we're going to go back and do chapter 2 later, and then we're going to do chapter 4. So we will be doing chapter 2 homework. It's just not until later. Again, it's all on the schedule. You can see sections from chapter 2 coming up later in the semester. There's also a question, direct message to me. It's what is the quiz going to be on? The quiz is going to be on 3.1 and 3.2 and a little bit of like review, a little bit of review, so just like use substitution. So basically, what's going to be on the quiz? Quiz A is what it's called. I'm numbering the exercise sets with integers, and I'm numbering the quizzes with letters. So what's going to be on quiz A? We're going to have the things we've been working on: review, use substitution. We're going to have integration by parts. We're going to have integrals involving trigonometry, including trig, application of trig identities. Okay, that's kind of the main thing. And then also just use substitution and integration by parts with trigonometric functions. Now, I'm going to put possibly trig substitution, which is actually a 3.3 topic. If I put something on there from section 3.3, it is only because I want the opportunity to look at your work and give you feedback on that topic. I think tomorrow is an opportunity for you guys to try something from 3.3 and submit it to me. I am hoping that you will all be comfortable with pushing forwards today and starting 3.3 a little bit early. If we do that, which I'm 90% assuming we're going to do, unless there's some strong objection and a bunch of questions you guys have about earlier stuff. I'm assuming we're going to do that. And if we do that, then on the quiz, the problem from 3.3 isn't going to be like heavily weighted when I'm grading. It's just going to be, it's really mainly there so that I have an opportunity to give you feedback on it. This is in keeping with my general philosophy of using assessments as primarily as a feedback mechanism, and the grade is sort of secondary. So anyway, yeah. So looking at the chat here, how difficult should we expect quiz questions to be? I always should aim for medium difficulty. There are really no tests in this class, so I'm not sure what you mean about test questions. We have quizzes and we have a final exam, so there's really one test. If anything, the final exam is where I put the easy questions, because there's a lot of them. So the quiz questions are generally going to be harder than the final exam questions, but like I said, medium difficulty. The hardest problems might be the ones we work on as exercises, or maybe on the in the homework. So for homework, speaking of homework, question from Ryan here: do we submit chapter 3 homework completion by section or as one unit? I want you to go ahead and submit your completion as one big unit. So just all the chapter 3 homework, when we get to the end of chapter 3, put in a percentage for the entire unit. Okay. And then when is quiz A? Tomorrow. Again, check the schedule if you missed that earlier. It's tomorrow. Tomorrow in class. Okay, so yeah, so I think you guys are so based on your based on your exercise set that I critiqued over the weekend, I think you guys are absolutely ready for the next topic. So my proposal is that we go ahead and push forward into 3.3. We'll just get a start on it today. And then, like I said, I can put like maybe a simple, none of the 3.3 problems are really simple. They're pretty much all kind of complicated. It's just the nature of trig substitution. But I thought I could put one problem on the quiz, and then it'll serve as an opportunity, an early opportunity for me to give you feedback. Sound good, everybody? Just going to pause for a moment while you guys consider that and give me feedback if you want to, or not if you don't. But already. Yeah, cool. So here we go. Trig substitution sort of sounds like something we've already done, because it sounds like doing U substitution where U equals like a trig function, but it's not. Trig substitution is kind of like a different spin on the idea of U substitution. It is similar to U substitution, but it kind of flips it around a little bit and uses trigonometric functions and trigonometric identities in a different way than we have so far. So in order to introduce this topic of trig substitution, I'd like to actually begin with an application problem that leads us into trig substitution, sort of like presents a situation where we would want to use it. Okay, so you're going to see it. I'm going to introduce it in a context. So here's the context. Suppose you've got a circle. There we go. Suppose this is a circle of radius 3. So if we center this at the origin, oops, then we can draw axes here. This would be 3, -3, -3, 3. Okay, so circle of radius 3. And then suppose what we're going to do is we're going to pick a value along the x-axis here and call that t. And then we are going to take a slice of this circle and try to compute the area of that slice. Yeah, I'm going to try to make it so that I can like fill it in. There we go. The idea is to try to compute the area of that slice right there. Okay, and then T is going to be sort of, you know, a variable that we can sweep across this circle, and we want to produce a function that outputs the area. So let's write that down as our goal. Find area as a function of that x value, which we're going to call T. It's not really a geometric formula. Like, you know, we've got a geometric formula for the total area of the circle. It should be pi r squared, right? Which is like 9 pi for a circle of radius 3. But that's not what we're talking about. We're talking about like cutting it and then, you know, cutting it and then taking a portion of that circle. So anyway, one approach to this problem is to say, let's just cut it in half and just talk about the like half of it, maybe just the, just like the upper half, perhaps, something like that, maybe. Okay, so if we just take the upper half, let's call, let's say, then we can say that the red area is basically going to be 2 times the green area. That makes sense? Split in half. So total area as a function of T should be 2 times that green area. And so now we can just focus on the green area. That is essentially the area under this curve and above the x-axis between -3 and T. So if we can describe this circle, like the top half of this circle, as a function of x, then we can integrate from -3 to T that function of x. Does anyone know how to describe a circle as a function of x? What's an equation for this circle? Well, x squared plus y squared equals 9 is an equation for the circle, first of all. That comes from the Pythagorean theorem, right? You guys remember learning equations for circles? You might have done it when you talked about conic sections in pre-calc. Yeah, a little bit. Well, x squared plus y squared equals 9 is the equation of a circle centered at the origin with radius 3, because 9 is 3 squared, right? So now to solve for, what we want to do here is solve for y. Y squared is going to be 9 minus x squared, and then y is plus or minus the square root of 9 minus x squared. And that plus or minus gives us the top and bottom half of the circle. So the top half of the circle here is the positive square root of 9 minus x squared, whereas the bottom is the negative square root of 9 minus x squared. Remember that you can't distribute the square root over that subtraction, so there's no simplifying here. We don't get like 3 minus x. That doesn't happen, right? Because you can't, that's just algebraically invalid, right? So instead, we just have these two. There's really no way to simplify these. This is what they are. So what we want to do is just focus on the top half and integrate that function, the square root of 9 minus x squared. We want to integrate that with respect to x from -3 to T, and that would give us this green shaded region, which we double to get the total red shaded region. With me so far? So the question then is, how do we integrate that? And as you can probably guess, this is where the trig substitution strategy is going to come into play. So attempts at U substitution fail. I'll just tell you that. If we had a little more time, if I wanted to take a little more time, it might be worth, attempting a couple of U substitution tries. If we had like an X out here, then we could do a U substitution, because if your U is 9 minus X squared, then the du is going to involve this X here, but we don't have that X there. Well, gosh darn it. That's right. So attempts at U substitution here fail. So we will introduce trig substitution, which is a new idea. Another good question about integration by parts. Diego suggests integration by parts. Don't think that works very well either. Because you get like now you have to integrate this, which when you integrate that, you get this, which is still a bit tricky. You've got an X squared up here as well as an X squared down there. So attempts to integrate by parts. I don't think that works well either. But I encourage you to try it. So I'll leave it as an exercise to you guys just to do on your own, not an assigned exercise, not an assignment, but just maybe it's worth taking something like that and trying all the other strategies we have learned so far to basically to convince yourself that none of them really work. And so that's why we're introducing a new strategy. So here's what we're going to do. We're going to let X equal, hang on a sec before I carry on. Let me just rearrange some things on my other page here so I can see my notes. We're going to let X equal 3 sine of theta. This introduces a new variable. With U substitution, we introduce a new variable called U. With trig substitution, we do the same thing, but traditionally, the new variable you're introducing is the input to a trig function. So we use theta, just because theta is, sort of the conventional letter to use for an angle. So X equals 3 times sine of theta. Now, this is different from your traditional U substitution, because with a U substitution, you're taking some portion of what's already there and setting it equal to U. Whereas in this case, we're just taking X itself, and then we're going to be inserting a larger expression involving the trig function in to where X is, right? So we're inserting that into X. See how that's different? It's like the opposite of a trig substitution. Instead of replacing a big chunk with U and making it simpler, we're taking just the variable and replacing it with a big chunk, which kind of sounds like it's going to make it more complicated, which it will temporarily, but it will give us access to trigonometric identities, which we can use to then simplify it later. Question of how do you determine which trig functions to use? And come back to that. Yeah, I want you to see this, see how it works out, and then we'll talk about why we chose to use sine, and in particular 3 times sine. So hold on to that question. All right, so if we're doing this variable substitution, we also need to do a differential substitution so that we complete the change of variables. So if this is X, dx is the derivative of this 3 times cosine of theta times d theta. So this would be your differential substitution. We need to make both of these substitutions in order to completely change the variable in this integral from x to theta. So what we get, we're just going to look at the integral of the square root of 9 minus x squared. And for now, I'm going to ignore the definite integral. We'll come back to that later. So this is going to become the integral of the square root. And then inside the square root, we have rather a lot going on, because we had to replace our x with 3 sine theta. And that whole thing is still squared. Okay. And then outside the square root, we also have a lot more going on, because it used to be just times dx. Now it's times all of that, everything that dx is equal to according to this variable relationship. So we have to replace dx with 3 cosine theta times d theta. All that. Okay. Now we have an integral to work with. Everything here is a little bit too big. Compress things. This part in particular, I think, can get smaller. All right. Okay, so now I'm going to go ahead and pull that 3 out over here. Might as well bring it out there. Now, inside my square root, I have to square both this 3 and the sine of theta, right? So I'm actually going to have 9 minus 9 sine squared theta, and then a cosine theta d theta on the outside. Okay. Now the fact that I have a 9 inside here means I can factor out a 9 from those two terms. So 9 times 1 minus sine squared theta, like that. Kind of being inconsistent with my parentheses. They shouldn't be inconsistent. Should be more consistent. Now, the square root of 9, right? If I can factor out a 9, I can split the square root into 2 square roots multiplied together. The square root of 9 is 3. So I have another factor of 3 that shows up right here from the square root of 9. Like that. So that 3 can come to the outside. I'll bring all this up here. So I have a 3 already from on the outside. I got another 3 on the outside, so now I have a 9 on the outside. And I just have this stuff, 1 minus sine squared theta times cosine of theta on the outside, and then times d theta. Okay. Following along so far? Is anyone wondering, why the heck are we doing this? How is this any easier than, how is this making it any better? This just looks like a train wreck so far, right? It's like, wow, I thought we had a hard integral, but now we have a really hard integral because it's got all these trig functions all over the place, right? Well, you'd be surprised perhaps, because like I said earlier, the reason we're doing this is really to give us access to trigonometric identities. So right here is the moment where we get to do that. So the Pythagorean identity, you know, sine squared plus cosine squared equals 1. If you rearrange it, tells us that cosine squared is 1 minus sine squared, right? So we can take this cosine squared here, oops, this part, and replace it with, sorry, I think I misspoke, but I meant we could take the 1 minus sine squared and replace it with a cosine squared. This is where it starts to get good. Ooh, all right. So having replaced the 1 minus sine squared with a cosine squared, we're down from 2 terms inside of that square root to only 1 term inside of that square root. And now we have a square root of a square, right? Which simplifies to, that's right, I knew you'd remember this, the absolute value of cosine of theta. All right. Now, we are going to wave our hands a little bit around that absolute value, because it turns out that the context in which we are doing this substitution allows us to assume that the theta value is between negative pi over 2 and positive pi over 2, and therefore cosine of theta is guaranteed to be a positive number. So its square root is just, so its absolute value is just itself, right? So we can omit the absolute value. Okay. So I'm going to put a little note in there, hand waving. Sine, so hand waving, in the original function, x ranges from -3 to 3. This corresponds to sine of theta ranging from -1 to 1, and theta ranging from negative pi over 2 to pi over 2. In this range, cosine of theta is always positive. So, oh, I forgot to put any carriage returns in that. Well, dang it. That's okay. We'll squeeze it in there. Fine print. Okay, that's okay. All right, so suffice it to say that the sort of context here will allow us to say, this is just cosine of theta times cosine. This is cosine squared. Okay. So now, we want to integrate cosine squared. This is something we have recently learned how to do, right? Cosine squared can be reduced using a trigonometric identity, the power reducing formula. This is 1 plus cosine of 2 theta all over 2. Okay, 1 plus cosine 2 theta all over 2. So what we have here is 9/2 times the integral of 1 d theta plus 9/2 times the integral of cosine of 2 theta d theta. Okay. Oops. Okay, we have 9/2 theta, and then this guy, we've got to do a little u equals 2 theta, du equals 2 d theta. So we'll divide both sides by 2 here and get another extra factor of 1/2 in there. And we end up with 9/2 theta from the first term there. Integrating 1 with respect to theta gives us theta, right? And then integrating cosine of u is going to give us negative sine. No, integral of cosine is positive sine. There we go. So still plus, but now we have an extra factor of 1/2. So instead of 9/2, it's going to be 9/4 sine of 2 theta with a plus c on the end. Now we are very nearly done, because after doing this trig substitution, right, we were able to rearrange things with a little bit of algebra, apply a trig identity. Then we got an integral that we can solve, cosine squared. We solved it using the strategies we learned about last week. And now we have an antiderivative, but the antiderivative is in terms of theta, right? So we don't really want an answer in terms of theta because our original integral was in terms of x. So we can undo our trig substitution. In order to undo it, here's what we will use. Let's go back to, it's going to compress everything here and get back to this part here. Let's talk about how we can undo this. Well, if x was equal to 3 sine theta, we can do x over 3 equals sine theta, and then theta is going to be arc sine of x over 3. Okay, theta will be, so that's just solving for theta in terms of x. That's just undoing that substitution there. And then, so that's going to help us part of the way. That's going to help us with this theta right here. That's going to, we can plug in a arc sine of x over 3 for that theta right there. Okay. But then technically we could do that over here too. I mean, we could just plug in arc sine for this theta as well, but we can do one better than that. We can do a little better. The sine of 2 theta right there, this sine of 2 theta, we can simplify that with the double angle formula. This is 2, you may remember this from a recent exercise set where you may have used this strategy. 2 times sine of theta times cosine of theta is sine of 2 theta, right there. Double angle. And now, remember how there were 2 steps in the process of solving for theta? Well, along the way there, we discovered that sine of theta is equal to x over 3. So this sine of theta right here is just x over 3. And we can make that substitution. The cosine of theta can likewise be replaced by something. Give myself a little extra space here. You know, let's go back to this. If you solve this Pythagorean identity for theta, it's the square root of 1 minus sine squared, right? And now we'll use, from that earlier substitution, we'll use sine of theta is x over 3 over here. Oops. So what do we get? That. And then here is reduce that slightly there, another 9/2. Sine of theta is x over 3. And cosine of theta is the square root of 1 minus sine squared, which is 1 minus x over 3 squared. And then we still have our plus c on the end. And that's it. That's wild. But that's our antiderivative. Pause and chew on that. Oops, sorry. Move that out of the way. There is a definite integral. We haven't gotten back to the definite integral. So far, this is just the antiderivative. You're right. There's a little more to this. I just walked you through a fairly long process of kind of, there was a change of variable and then a change back, right? So we went over to theta and then we came back to x. And doing that, going back and forth, involves like inverse trig functions and substitutions and just a lot. Trig identities. There's a lot going on here. Okay, yeah. So Solon's got a good question. Why did we end up using just x over 3? The reason is because let's zoom in on this right here. X equals 3 sine theta was the original substitution we made. So x over 3 equals sine theta. If you want to solve for theta, you can do an arc sine. But back over there, we had this sine theta popping up in our answer, so we can replace it with x over 3. No need to use the arc sine if you already have a sine, you know, in your work, right? So over here, when we saw sine theta, just x over 3. And then the cosine theta, similarly, we put that in terms of sine and then just stick the x over 3 in for sine. Okay. This can be simplified a little bit, but I just want to show you that this is pretty much exactly what Wolfram alpha will tell you if you ask it, what is the integral of the square root of 9 minus x squared? This is just a slight algebraic simplification of the answer that that we've got here. Okay, slight algebraic simplification, just like dealing with that fraction inside there. You get like a 9. You pull a 9 out, and the 9s cancel, and there's some 3s that are gonna. There's some 3. I think that 3 cancels out somehow. Yeah, the 3 and the 9 cancel, and then you know, here's your arc sine term over here. But it's very similar. That's exactly what it is. So, you know, there you go. You type a similar integral into Symbolab or Mathway or anything, and they're all going to tell you got to do a trig substitution on this one. Okay, that's so that's why. So we are learning this. Okay, all right. So now, Shai just reminded us, wasn't this a definite integral? Ah, yes, it was. So now let's pull in technology to evaluate this for us. Let's type in what we got. So let's call it g of x or something. And I'm going to type in our answer we got done here, which is, let's see, 9/2 arc sine of x over 3. Oops, sorry. X over 3. Here we go. And then plus, there's a 9 and a 3 that I'm going to reduce there. So for this fraction, I'll do 3/2 x, and then square root of 1 minus x over 3 squared. All right, so there is our function, and we wanted to know, like, this function evaluated at -3 and t. Right? See the t and the -3 there? You want to be able to plug those in. Okay. So let's back up for a second. If this is supposed to be our area function, okay, if I call this like a of x, or I could even call it a of t, actually, because we might want to replace the x with a t to produce an area function. Notice that if I do like a of -3, I do not get 0. Okay, in our picture over here, if you ask the area function, what is the area when t equals 0? Okay, if this t here, if this t were, sorry, I think I said 0, but I misspoke. If this t were equal to -3 over here, then the area should be 0, right? Because it'd be -3 up to it'd be -3 down here, and it would be -3 up here. So that area should be 0. Yeah, so what's going on here is not that our answer is wrong, but that we're missing a plus c, right? And we need to adjust our antiderivative to have the right plus c on the end. That makes sense? So I'm going to get us a new whiteboard, and we'll just wrap this up on the next page. Okay, here we go. Okay. Oh, I forgot an x. 3/2 x times the square root of that. Okay. Cool. So we want to say if this is going to go here, let's get rid of that plus c for a moment. If this is going to go from -3 to t, we want to do this jazz at -3 and at t. So plugging in the t, we get t, and t, right? But then minus a constant term, right? And the constant term is whatever we get from putting in -3 for x. So 9/2 arc sine of -3 I feel like I made a mistake here. This isn't arc sine of x. This is arc sine of x over 3. Yep. Thank you. Yep. Isa just got that for us. Thank you, Isa. Yep. T over 3. There we go. That's better. Because I was about to say arc sine of -3 is not, that doesn't make any sense. It's over 3. There we go. That is what it's supposed to be. I think I just didn't copy the whole thing correctly from the previous page. Plus 3/2 times -3, and then this stuff. Didn't give myself quite enough space. -3 over 3 squared. Okay, so some of this simplifies up nicely because here we have 1 minus -1 squared square root. This is 1 minus 1. This is 0. So that means that this whole term is times 0. So that part's nice and simple. So we just have to worry about what's going on over here. 9/2 times the arc sine of -3 over 3, which is -1. How does arc sine work? And this is something you would have learned back in pre-calc, but it's probably been a long time. Arc sine always gives you an output in this range from -pi/2 to pi/2. And remember that the sine of an angle is the y coordinate of the corresponding point on the unit circle. So we want to know when y equals, -1, which would be down here actually. Y equals -1. And the point, the angle that produces a sine output of -1 is -pi/2. So this means this is 9/2 times the arc sine, which is -pi/2, or in other words, -9 pi over 4. Now we are subtracting this. So that's going to become a plus. So we have plus 9 pi over 4. And that should do it. If I go back to my area, if I go back to this this thing, if I add 9 pi over 4, then that shifts the whole thing up by exactly the right amount, so that when you plug in -3, you get 0. Now, I think, is this correct, or is this actually, do I actually need to multiply it by 2? Do I need to multiply this by 2? Did we ever multiply by 2? I don't think I've multiplied by 2 yet. So actually, I should take all of this times 2. There we go. Or if I distribute that through, I could distribute the 2 across there. It would cancel out a bunch of things. We could do that and get rid of this 2. Cancels that 2. It's going to cancel this 2. And then it's going to cancel the 2 from here. And there we go. So now here's the other. So we can check one end. At one end, we get negative. At -3, we should get 0, right? Because looking at our picture, the circle of radius 3, we should have a of -3 equals 0. And check on that. Now, the other thing we might want to check is a of +3. What should the area of the whole circle be when we get all the way to +3? Pi r squared, 9 pi. So let's check our work. If I do a of +3, we have a number. Is that equal to 9 pi? If we compare it against 9 pi, we see that it is. So check. Awesome. So on this picture, we could do we could graph like y equals 9 pi if you want. And we can see this is the area function, and it goes from 0 up to 9 pi as the t value sweeps across the circle. So check. So I never got around to taking attendance today, but what I will do is I'll just look at the Zoom log today to see that you were here. That might be what I do going forward, because I thought about various ways that you could check off your own attendance, but I would still have to just look at a document and copy over the results. And I mean, Zoom keeps a log of who attended, who's here, right? So so I can just look at that. I think I might just do that. It seems just equivalent. The only difference would be whether I make you actively check a box or if I just have it be a passive thing. And I think I'm okay with it being passive. Oh yeah, so Josh brings up that point that was raised earlier. Somebody asked, in fact, it was you, Josh. Yeah, how do you determine what trig function to use? There are patterns, in certain, this was a square root of something minus x squared. It turns out you always want to use sine or a multiple of sine in that case. If it's x squared minus something, then you use secant. And if you have if you have something plus x squared, you can use tangent. It's just, we'll go over all that Thursday. Okay. And then one more question in the chat here. Do you get to use the trig identity sheet and the differentiation and integration rules sheet on the quiz? Yes, definitely the trig identities sheet. And I'm going to say yes. I think I'll let you use the differentiation and integration rules sheet as well. So you get to use those two on the quiz. All right. Bye, folks. Have a good one.
I have a question.
Yeah, is that Ali?
Yep.
What's
I
up?
came in late, so we have a quiz tomorrow, right?
Yes, quiz tomorrow.
And is it gonna be like the exam? No, not the exam. The example work exercise. So,
Yeah, it'll be really similar to what you had on your recent exercise set. Yeah. So it'll be a little bit of review of like U substitution. It'll be some integration by parts, and it'll be some integrals involving trig identities.
all right.
Yep.
Yeah.
Bye.
I had the same question as Issa.